Hello and welcome to Math Zone African Motives. Today, we're going to dive into a fundamental topic in electrotechnics, magnetism and electromagnetism. By the end of this video, you will be able to define and describe magnetic fields, understand different types of magnets, explain the magnetic effects of electric currents, and calculate the force and other key properties in a magnetic circuit. So, what is magnetism? It's simply the force exerted by magnets when they attract or repel each other. This force creates an invisible area around the magnet called a magnetic field, where other magnetic objects can experience attraction or repulsion. To help us visualize this, we use a concept called magnetic field lines or magnetic flux. Magnetic lines of flux are a visual tool, like a map, that shows us the direction and strength of the magnetic field. Magnetic flux is represented by the Greek letter phi, and its unit of measurement is the Weber, abbreviated WBE. Let's look at the magnetic field around a permanent bar magnet. Here we see a diagram of a bar magnet with a north pole and a south pole. Notice the lines with arrows. These are our magnetic flux lines. They flow out from the north pole, curve around the magnet, and enter the south pole. These lines are continuous, forming closed loops that pass through the magnet itself, but for our visualization, we focus on the external field. Now let's explore the fundamental properties of these magnetic field lines. Understanding these characteristics is key to understanding how magnets work. First, magnetic flux lines always flow from the north pole to the south pole. We already saw this in our bar magnet diagram. Inside the magnet, they complete the loop from south to north, but the external field direction is north to south. Second, as we mentioned, these lines form continuous closed loops. They don't just stop in space. Third, they act like stretched rubber bands, always trying to shorten themselves. This property explains why opposite poles attract. The flux lines between them shorten, pulling the magnets together. Fourth, and this is a critical one, magnetic lines of flux can never intersect or cross each other. This is because at any single point in a magnetic field, the field has a unique direction. If lines crossed, it would imply two directions at that point, which is impossible. Fifth, magnetic lines that are parallel and flow in the same direction will always repel each other. This is why similar poles repel. The flux lines between them are in the same direction and exert a repulsive force, pushing the magnets apart. Finally, magnetic lines of flux are vector quantities. This means they have both a magnitude or strength and a direction. This vector nature is crucial when we talk about combining fields later on. Now that we understand what magnetic fields are, let's look at the different types of magnets. There are three main categories of magnets: natural magnets, permanent magnets, and electromagnets. Let's start with natural magnets. Natural magnets are what we find in nature. The most famous example is lodestone, which is a type of mineral called magnetite. This rock is naturally magnetized and was the first type of magnet discovered by ancient civilizations. You can see what lodestone looks like here. Next, we have permanent magnets. Unlike natural magnets, permanent magnets are man-made. They are created by taking certain metals like iron, nickel, or cobalt and exposing them to a strong external magnetic field. The process is called ferromagnetism. Ferromagnetism is the property of these metals that allows them to be magnetized. After the external field is removed, the metal retains its magnetism, becoming a permanent magnet. A typical horseshoe magnet, like the one you see here, is a classic example of a permanent magnet. Finally, we come to the most important type for our study of electrotechnics: the electromagnet. An electromagnet is temporary. It gets its magnetic field from an electric current. As soon as the current is turned off, the magnetic field disappears. Here's a simple diagram. A coil of wire, called a solenoid, is wrapped around a ferromagnetic bar. When the battery is connected and the switch is closed, current flows, and the device becomes a magnet. When the switch is opened, it loses its magnetism. This temporary nature makes electromagnets incredibly useful for controlling magnetic forces, a principle that is the foundation of things like electric motors and relays. We've seen that electromagnets are created by electric currents. This brings us to a crucial concept: electromagnetism, the study of the relationship between electricity and magnetism. At its core, electromagnetism is the study of electromagnetic forces. A Danish physicist named Hans Christian Ørsted discovered in 1820 that when an electric current flows through a conductor, it produces a magnetic field around that conductor. What does this magnetic field look like? Around a straight conductor, the magnetic field takes the form of concentric circles, centered on the conductor itself. So we have a circular magnetic field, but which way does it go? The direction of the magnetic field lines around a current-carrying conductor can be found using the right-hand rule. The right-hand rule for a conductor states that if you hold the conductor in your right hand with your thumb pointing in the direction of the current, the curl of your fingers will point in the direction of the magnetic field. Let's see this in action. If the current is flowing upwards, your thumb points up and your fingers curl counterclockwise. This means the magnetic field around the wire also travels in a counterclockwise direction. Another rule that gives the same result is the screw rule. Imagine a screw traveling in the direction of the current. The direction you turn the screwdriver is the direction of the magnetic field. To make diagrams clearer, we use special symbols to show the direction of current when it's flowing towards or away from us. We use a circle with a plus sign in the middle. Think of the feather end of an arrow flying away from you. This symbol means the current is flowing away from you or into the page. And we use a circle with a dot in the middle. Think of the tip or point of an arrow flying towards you. This symbol means the current is flowing towards you or out of the page. Now let's apply these rules to a coil, also known as a solenoid. A coil is used to concentrate and strengthen the magnetic field from a current-carrying conductor in a smaller area. When current is passed through a coil, it is said to be excited or energized, and it becomes an electromagnet. How can we make this electromagnet stronger? There are 4 main ways. First, we can increase the number of turns in the coil. More turns mean a stronger field. Second, we can increase the current flowing through the coil. Third, we can use thicker wire. This is because thicker wire has less resistance, allowing more current to flow. And fourth, we can insert an iron core into the coil. Iron is a ferromagnetic material that helps guide and concentrate the magnetic lines of flux. For an electromagnet, we need to determine which end is the North Pole. For this, we use the right-hand grip rule. The right-hand grip rule for a coil states that if you grip the coil with your right hand so that your fingers point in the direction of the current, your outstretched thumb will point to the North Pole of the electromagnet. Let's demonstrate. If the current flows around the coil like this, your fingers follow that direction. Your thumb points to the left, so the left end of the coil is the North Pole and the right end is the South Pole. We've discussed magnetic flux, which is the total magnetic field passing through an area. Now let's talk about how concentrated that field is, which we call magnetic flux density. Magnetic flux density is simply the amount of magnetic flux passing through a specific area. It's represented by the symbol B and measured in Teslas, abbreviated T. So a flux density of 1 Tesla means there's 1 Weber of magnetic flux passing through an area of 1 square meter. Imagine a magnetic field between 2 poles. The flux density B is a measure of how many flux lines are packed into that area. To calculate this, we use a simple formula. The formula for magnetic flux density is B equals phi divided by A. Here, B is the magnetic flux density in Teslas, F is the magnetic flux in Webers, and A is the area in square meters. Remember to always work with the correct units, especially when dealing with prefixes like milli. Let's work through an example to see how this is applied. Example 125 states, a magnetic flux of 55 milliwebers produces a magnetic flux density of 1.75 Teslas in the air gap between 2 magnetic poles. Calculate the area of this air gap. First, we write down what we are given. The flux phi is 55 milliwebers, which we must convert to webers by multiplying by 10 to the power of minus 3, giving us 0.0055 webers. The flux density B is 1.75 Teslas. We start with our formula. B equals phi over A. We need to find the area A, so we rearrange the formula to make A the subject. This gives us A equals phi divided by B. Now we substitute our values. A equals 0.055 divided by 1.75. Calculating this gives us approximately 0.031 square meters. So the area of the air gap is 0.031 square meters. So far, we've explored the magnetic field around a conductor. Now let's ask a more interesting question. What happens if we put that current-carrying conductor inside another magnetic field? The answer is it will experience a force. This interaction between two magnetic fields produces a force, a push or a pull, that can make the conductor move. Let's visualize this process step by step. First, let's establish our main magnetic field using two bar magnets. Here we have a north pole and a south pole. This creates a uniform magnetic field between them, with flux lines running from north to south. We'll call this our main magnetic field. Next, let's introduce our current-carrying conductor. We place a conductor, shown here as a dot with a plus sign, which means the current is flowing away from us, into the page. According to the right-hand rule, this current creates a magnetic field around the conductor. In this case, with the current into the page, the field is clockwise. We'll call this the secondary magnetic field. Now for the key step. We merge the two diagrams. We combine the main magnetic field of the magnets with the secondary magnetic field of the conductor. Because magnetic field lines cannot intersect, the secondary field of the conductor distorts or pushes and pulls the main field of the magnets. Above the conductor, both fields are in the same direction, so they work together to form a stronger, more concentrated field. Below the conductor, the fields are in opposite directions, causing them to cancel out and form a weaker field. What is the consequence of this imbalance in field strength? Remember, magnetic flux lines behave like stretched elastic bands. The stronger field above the conductor, with its bunched-up lines, acts like a tight rubber band that wants to release its tension. The weaker field below offers less resistance. This stronger field above pushes down on the conductor. Therefore, a downward force is exerted on the conductor. From this, we can conclude that for a force to be produced on a conductor, we must have two interacting magnetic fields: a main, external field, and a secondary field created by the current flowing in the conductor. So, we've seen that a force is produced. How do we calculate its magnitude, and how do we find its direction? First, the magnitude of the force. The strength of this force depends on several factors. The formula for calculating the magnitude of this force is F equals B times I times L times the sine of theta. This is the motor principle, which we will see in action in motors. Let's break down the variables. F is the force in newtons. B is the magnetic flux density in teslas. I is the current in amperes. L is the length of the conductor that is inside the magnetic field in meters. And theta is the angle between the direction of the current and the direction of the magnetic field. There's a very important special case. What if the conductor is placed at a perfect right angle, or 90 degrees, to the magnetic field? In this situation, the angle theta is 90 degrees. The sine of 90 degrees is exactly 1. So the formula simplifies to F equals B times I times L. This gives the maximum possible force for a given current and field. Now for the direction of the force. To find this, we use a different hand rule called Fleming's left-hand rule, also known as the motor rule. Hold the thumb, first finger, and second finger of your left hand at right angles to each other. Your first finger points in the direction of the main magnetic field from north to south. Your second finger points in the direction of the current. Then your thumb will point in the direction of the force exerted on the conductor. Can we reverse this force? Yes, we can. There are two methods to reverse the direction of the force. First, we can reverse the direction of the magnetic field. This is like switching the magnets so south is on the left and north is on the right. Second, we can reverse the direction of the current flowing through the conductor. Both of these actions will reverse the force. This principle of reversing the force by reversing the current is fundamental to how DC motors work. Let's apply our new knowledge of the force on a conductor to a practical example. Here is example 126. Determine the magnitude of the force exerted on a conductor that is 275 millimeters long, carrying a current of 9.8 amperes, and placed at right angles to a magnetic field that has a uniform magnetic flux density of 2.25 teslas. As always, the first step is to identify the information given in the problem. We are given the length L as 275 millimeters, which we must convert to meters by dividing by 1,000, giving us 0.275 meters. We are given the current I as 9.8 amperes. The magnetic flux density B is given as 2.25 teslas. Finally, the problem states the conductor is placed at right angles, which means the angle theta is 90 degrees. Now we select the appropriate formula. Since the conductor is at right angles to the field, we can use the simplified formula. The simplified formula is F equals B times I times L. This is because the sine of 90 degrees is 1, so it drops out of the equation. The next step is to substitute the given values into the formula and solve for the force F. Plugging in our values, F equals 2.25 times 9.8 times torr 275. Calculating this gives us an answer of 6.06375 newtons. Rounding our answer to 2 decimal places, we find that the magnitude of the force exerted on the conductor is 6.06 newtons. Remember to always include the unit newtons in your final answer. Now let's explore 3 more key concepts that are central to understanding magnetic circuits, which are analogous to electric circuits. We will define magnetomotive force, magnetic field strength, and magnetic reluctance. You'll notice these have direct parallels to electromotive force, electric field strength, and electric resistance. Let's start with magnetomotive force. Magnetomotive force, abbreviated as MMF, is often called the magnetic potential. It's the driving force that produces magnetic flux in a magnetic circuit. Its unit is ampere turns, GAT. The formula for MMF is very simple and intuitive. Magnetomotive force equals N times I, where N is the number of turns in the coil and I is the current flowing through it. So, MMF is the product of the number of turns and the current, measured in ampere turns. Next is magnetic field strength. Magnetic field strength, or H, measures the intensity of the magnetic field along a certain path. It's defined as the magnetomotive force per unit length of the flux path. Its unit is amperes per meter, AM. The formula for H is MMF divided by L, where L is the length of the magnetic circuit. We can substitute Ni for MMF to get a more detailed formula. H equals Ni over L. This shows that the field strength is directly proportional to the ampere turns and inversely proportional to the path length. Finally, let's define magnetic reluctance. Reluctance, represented by the symbol S, is the opposition to the magnetic flux in a magnetic circuit. It is the magnetic equivalent of electrical resistance. The formula for reluctance is S equals MMF divided by phi, where phi is the magnetic flux. You can think of this as Ohm's law for magnetic circuits. Reluctance is like resistance. MF is like voltage, EMF, and flux is like current. Reluctance is measured in amperes per Weber, AW. Let's put our new magnetic circuit formulas into practice with an example involving reluctance. Example 127 states, an iron ring with a reluctance of 63.5 kiloampere turns per Weber has a 500-turn coil wound around it. A current of 5.5 amperes is passed through the coil. Calculate the magnetic flux produced by this magnetic circuit. Again, our first step is to identify and list the known values, converting units as necessary. We are given the reluctance S, which is 63.5 kiloampere turns per Weber. The prefix kilo means 1,000, so we write this as 63,500 ampere turns per Weber. The number of turns N is 500 and the current I is 5.5 amperes. Our goal is to find the magnetic flux phi. We will use the formula for reluctance and then the formula for magnetomotive force. We know that reluctance S equals MMF divided by flux phi. We also know that MMF equals N times I. We can substitute the Ni expression for MMF into the reluctance formula. This gives us S equals Ni over phi. Now we need to rearrange this combined formula to solve for phi. By cross-multiplication, we get S times phi equals Ni. Then we divide both sides by S to isolate phi. So, phi equals Ni divided by S. Finally, we substitute our given values into this rearranged formula. Phi equals 500 times 5.5, all divided by 63,500. Calculating the numerator, 500 times 5.5 is 2,750. Dividing 2,750 by 63,500 gives us approximately 0.0433 Webers. The problem asks for the answer in milliwebers as well. To convert from Webers to milliwebers, we multiply by 1,000, which gives us 43.3 milliwebers. Either answer is correct, but the textbook provides 43 milliweb as a rounded value. Let's quickly recap what we've covered today. We started with the basic definitions. We learned that magnetism is the force between magnets, and we use magnetic field lines or flux to visualize the area of that force, which is called a magnetic field. We explored the key properties of these flux lines, such as flowing from north to south and never intersecting. We then moved to the heart of electrotechnics, the magnetic effects of electric currents. We saw how a current-carrying conductor creates its own magnetic field, and we learned to find its direction using the right-hand rule. We discussed how to make an electromagnet from a coil and find its north pole using the right-hand grip rule. Finally, we learned about the force on a conductor in a magnetic field, calculated it with F equals Beal sin theta, and found its direction with Fleming's left-hand rule. We also introduced three important concepts for magnetic circuits: magnetomotive force, magnetic field strength, and magnetic reluctance, showing their formulas and worked through an example. Understanding these principles is fundamental to so many electrical devices, from motors to transformers. Thank you for joining this tutorial. If you found it helpful, please consider liking this video and subscribing to Math Zone African Motives for more content. And don't forget to practice the activity problems to solidify your understanding. Until next time.